Welcome back. And in this second video for neural networks, we want to discuss only a few things that are especially of relevance when you really want to define neural networks and you want to estimate them and use them to make, for instance, predictions. And like the stuff you would do with real data and facing real tasks. First of all, let's just go to the point where we left at the last video. So at the moment we know that a neural network is something where we have feature information as always. So we have a certain set of feature variables and the realizations for a single observation. Then we learned that we simply combine those feature realizations in very similar ways than we are already used to when we work with typical regression models, but we combine them first to generate something which is called hidden neurons, and then at some point we can use those hidden neurons as we are used from our base models that we discussed in the beginning of the semester to again either generate a prediction for a regression task, a prediction for a binary classification task, or even a prediction for a multi-class classification task. That's what is called the forward pass. What you already should know is that as before, we have certain parameters that need to be calibrated, that need to be defined when we want to work with a neural network. The more neurons, the more layers we want to have in our model, the more parameters we are going to, or we need to calibrate. Calibrating more parameters often works obviously better if we have more data samples. So this is something that you should have in mind. Typically, especially as we have so many parameters in highly complex and big neural network structures, it is of great importance that we have enough and sufficient observations and data samples in order to all train these immense amount of parameters. The training itself is usually done by gradient descent methods, okay, by variations of gradient-based numerical optimization. So as before, depending on the task we are facing, we are using a loss function, and the loss function is minimized by calibrating, by specifying the parameters of the neural network. And the minimization is done by the numerical optimization technique, which is called gradient descent. When it comes to neural networks, it is very common to work with stochastic gradient descent, or more concrete with stochastic mini-batch gradient descent. What's behind the idea here is that, let me just go there, I think I've written it down somewhere here, or not, I didn't, but let me just elaborate this the second here. So what you usually have when we estimate, or what the package that we're using is doing when it estimates the neural network, for all the parameters in the network, it generates the partial derivatives. So the partial derivative with respect to the loss function, or the partial derivative of the loss function with respect to each of the parameter values. So especially, this is kind of, it is not easy, but it's easy for the computer because it can do it in a very general way, because the only thing we are using when we build up the neural network, so when we have the forward structure, is a composition of individual functions. And the composition of individual functions can easily be differentiated by applying the chain rule, and that is what is done by the packages. And this is done. This is called backpropagation, because in comparison to the forward pass that we have when we want to make a prediction, you can imagine this like you're starting with the input information and going through the network forwardly in order to make a prediction. Where now we want to understand, for instance, how the parameters of the first layer in our network somewhat impact the prediction. And by this way, the loss function, so that's basically the partial derivative, how sensitive is the value of the loss function with respect to each of the parameters, then we need to go backwards with the chain rule in order to derive the derivatives, the partial derivatives here. And luckily for us, this is somewhat easy for the computer, as long as we are applying only the chain rule and as long as we have differentiable functions, which is usually the case here. So this is something you don't need to worry about. So everything you learned so far here remains the same and is done in a way that you really, you will not even notice where and when it is done, because it's done, under the hood when using your computer package. But what you at least will see when the package we're using is doing this iterative process of gradient descent optimization is that usually it does not, like at a single iteration step. A single iteration step consists of determining partial derivatives and using the information of those derivatives in order to update the parameter values such that the value of the loss function will be minimized. Like in the first step, in the way that we discussed it in the beginning of the semester, is that we thought about this like using all the data samples and deriving the partial derivatives with respect to a certain parameter, but hereby use the information of all the data samples. Especially when we have big data sets that can be computationally quite intense. And this is why another extreme version of this would be at a single iteration process, we randomly pick one observation of our data set, then determine the partial derivative and only use the information of the partial derivative of that individual observation in order to improve the parameter value at a single iteration step. And this is like the other extreme. This would be the stochastic gradient descent. And the mini batch stochastic gradient descent is something, assume we have 1,000 observations, then we randomly pick 100 observations, we derive the partial derivatives and use the information of those 100 observations in order to improve the parameter estimate as a single iteration process. And this is something what you will see. So what the package we're using is doing here, for instance, if we have 1,000 observations, it's 10 for 10 at one epoch. For 10 times, for instance, we use a mini batch of 100 observations. So 10 times we will randomly take 100 observations. At each time, the partial derivatives are derived on the basis of those 100 observations, and the update of the parameters is done on the basis of the derivatives of those 100 observations. This is done then, for instance, for 10 times, such that at a single epoch we are using the same amount of observations that is given by the whole data sample or by the whole training sample. Nevertheless, when we randomly draw here, replacement is allowed, so it is not guaranteed that really all individual observations are used at one epoch. And then for multiple epochs, this is done again and again and again. So hopefully over time, by using different observations and the information of the partial derivatives, so that just means using the information of the loss function here in order to further improve the model. More and more our parameters are going to be calibrated such that the loss function is reduced, and we stop at some point when we think this is enough and the loss function is low enough, and no loss function which is low enough simply means that our parameters learned how to generate the best possible predictions for the training data that we're using. And sorry about that, this took a little bit longer than planned, but this is like in words what's happening when we click on the fit function of the package that we're going to use. Okay, but still, like if the formal explanation of the backpropagation step is, I try to write this down here with a simple example, and you can take a look at this, and hopefully it will further deepen your understanding. But for the moment, as I said before, this is kind of also advanced stuff. And for me, at the moment, it would be enough that you know that neural networks are, calibrated in a way that is making use of the gradient descent method, and then you at least have an idea of what the gradient descent method does in order to optimize a function. Then what you should know are then like two things. First of all, it is very recommendable to standardize your data before you fit and estimate a neural network. We already discussed about this when we talk about the fundamental concepts, but here for the application of neural networks, it is kind of quite important that all of your feature variables are on a comparable value range. Basically, there are some real mathematical reasons behind that, but more intuitively, this just enhances the stability of the estimation process. So like that's enough if you know that for the moment, really. But always remember to standardize your data before you estimate the neural network. Otherwise, this really can have a very negative impact on the calibration of your neural network. Furthermore, the question, so you're completely free what you decide, how many neurons, how many layers, and so on. But for common forward neural networks, it is, I would say, not recommendable to use more than 2 or 3 hidden layers, kind of depends. And that is due to the so-called vanishing gradient problem. Let's not talk about that too much into detail, but what stands behind here is that if you're having multiple layers behind each other, and when you need the partial derivatives, for instance, for the parameters of the first layer, you will have to backpropagate through many layers, and backpropagation will make use of, make the chain rule and multiplying numbers with numbers, and especially with certain activation functions that are commonly used for neural networks. Those numbers are kind of small, typically somewhere in between 0 and 1. And if you multiply again and again numbers which are small, the numbers will get smaller and smaller. So the partial derivative will be approximately to 0, and the parameters in your first layer will not really be changed by the gradient descent method because the gradient is approximately equal to 0. And that's what is what we refer to as the vanishing gradient problem. That's why it is not recommendable usually to use more than 1 or 2 hidden layers, especially also in combination with the understanding of the universal approximation theorem, which says that you can, typically a hidden layer should be enough, or at least 2. Let's say it like this, not make it more any complicated. And also at the same time, there's not only the vanishing gradient problem, there's also the exploding gradient problem you may face, because sometimes, partial derivatives, they can be very steep, leading to very high values, leading to very big updates, very big changes in your parameters, which can also have a negative impact during the numerical optimization process. Those are all things you just need to hear about. So usually you are good in the beginning with just using, for instance, a single hidden layer or at least 2 hidden layers, standardize the data. Then me personally, I never experienced the vanishing or the exploding gradient problem when I did that, okay? Doesn't mean that this is 100% guaranteed that it will never happen, but that's why it's also important for you, and I will show you in a minute how you can do that, to monitor the loss during the training of your neural network, because if the network isn't learning anything, you will realize that your loss value is not really getting smaller during training. And the exploding gradient problem, I would say you can identify that, for instance, if you have very big changes in the loss value, then being lower, again being tremendously higher, or like being lower in the beginning and then increasing again during training. Those are things that are you should pay attention to those things, but I will show you in a second where to look at. Okay, then basically what's the most important question is, of course, in theory, this may all sound very complex to you, but I will show you that this is very easy to estimate and define neural networks in reality when we're using certain packages that are available to us, especially when we use Python, but would also be available, for instance, if you're a R user or something. There are different, basically what you need for a neural network to be defined and to be estimated are just 2 things. You need basic math operations like matrix multiplication and those activation functions. That is what you need in order to generate predictions. And also what you need to calibrate a neural network is a good automated process of deriving the partial derivatives. So you need a good automatic differentiation packages. And there are many Python packages which really make a tremendous job in doing those tasks. Examples are TensorFlow or Torch, for instance. Or like JAX is also, I would say, a more low-level library, which is really doing this in a highly efficient and very good way for the common user, like I would consider myself. But even more easy is to use the keras API here, which is on top of those automatic differentiation libraries and makes even the definition and the estimation of the neural networks more easy. And yeah, I will show you in a second. So we're going with the keras API, which makes usage of other libraries. We will use the keras API on top of the TensorFlow library, just because I'm used to it, but obviously you could also use other libraries here. Doesn't really make that of a big difference nowadays, and I think it's more or less how you learn it and on your personal preferences. Okay. Then before we take a look at the code, where I want to just quickly show you like how you can define a neural network. Just one thing that needs to be stated at least now at this point during the course, and that is neural networks are really able of capturing complex relationships, especially if we define them with, for instance, many hidden neurons and with at least one or two hidden layers. Then they really can be adjusted to the data almost perfectly. And that can cause big problems, because if we adjust the model to our training data almost perfectly, and with our understanding of the reality behind it, that we know that the data to a certain degree are driven by deterministic relationship, hopefully, between the feature variables and the target variables, but also are plagued by randomness, then if we adjust the model perfectly to the data, means we also adjust the model perfectly to the randomness that is only specific to that training data, and this will not happen in the same way when we have new data. So if we estimate and adjust our model too perfect to the data, then we will overfit the model, which means the part of the randomness that will be different in the future is exactly that where we will make mistakes when we're making future predictions. So that is why we want to make sure that we do not overfit our model. Overfitting is general, dangerous, or can be a potential threat for all the models, especially those that are, capable of capturing really flexible, complex relationships. For instance, also tree-based models we discussed so far. Here we had, for instance, like the pruning approach, with kind of had a tendency to regularize the model and make sure not to overfit. But there are like other things. I would say for instance, for the linear regression model here, the potential threat is more like underfitting, that the model is too easy and not capable of capturing the complex relationship in reality. But for neural networks, you need to make sure not to overfit. And at least to make sure that you do not overfit, you need training data and test data, at least. Sometimes it makes also sense to also have validation data when you use a hyperparameter tuning approach. And you really need to monitor the training data as well as the test data during the training process, and make sure that the performance of the model for the test data is comparable to the performance of the training data. Once you realize that your model is very good for the training data but performs poorly for the test data, you're likely to overfit, and then you need to do something against it. And two things you can do against it when you are working with neural networks is either use a regularization that can be done, I think, layer-wise or to the overall model, or you can do something, especially what is relevant for networks, which is called a dropout. Okay. So first of all, regularization is something that you can basically also use for all the models we discussed so far. So whenever we have a loss function and a model that depends on parameters, we add to the loss function another term that is the higher the more variables we're using, or the higher the parameters in the model are. So we have the L2 regularization scheme. So here, we have the loss function, and we have the sum of the squared values of the parameters that are used in our model. And this is weighted by a lambda parameter. This parameter is defined by us. The higher we set it, the more we punish a model that uses higher or more parameters here. And so here basically what we do is we generate a trade-off. First of all, assume that some variables in the model for which we have if we use all the variables in the model, then our loss function is in tendency lower or decreasing. But it has to be significantly lower, because if we use all the parameters in the model, all the variables in the model, then we also need to make sure that all the parameters of the model are non-zero, which increases the second term here. So we have a trade-off. Using all variables in the model decreases the first part here, but increases the second part. So if there are variables in the model which really do not cause a significant decrease of the loss value, then it may not worth it to set its value to non-zero, and it's better to set its value, for instance, to 0 or to a very small number. And that is the trade-off we are facing when we're using the regularization as defined here. L2 regularization is the L2 norm of the parameter vector. This just means we have the sum of the squared values of the parameters. The L1 regularization is the sum of the absolute values of the parameters in the model. The kind of this, like, there's not like the better regularization scheme. Depending on the task, depending on what we want to do and what we want to achieve, it's good to pick one of those two. But that's not the important aspect at this moment. The important aspect at this moment is that you know now that there is something which is called regularization, and here L2 and L1 regularization kind of creates a trade-off. So whenever you are using a variable in the model, which means setting its parameter value to non-zero value, it should be really worth it, such that it significantly decreases the loss value of the model. Okay, so that is like, we want to, with this introduction of this punishment here, we just want to make sure that our model questions itself, it is really worth it to use a specific variable. Okay, you can picture it like that. Another way is the dropout, that especially is useful for neural networks. So if you have a dropout is just that you randomly select a fraction of the neurons during a single training step or single training iteration and set them to 0. That just means if you, for instance, go back to the beginning where we had the illustration of the neural network, in a single iteration step, then we, for instance, pick here like the first and the last neuron and set it equal to 0. That also makes the parameters that relate the feature variables to those neurons to be equal to 0, because a parameter value times 0 is 0. So you will lose some linkages here. You will lose some of those errors. So some of the relationships then will be ignored for a single iteration step during training the model. And that kind of manipulates our model and forces it not to use all the available knowledge at each single step once we are training the model. So another, if you want to say, manipulation to make it harder for the model to learn the relationship in the training data. But that is what we are intending to do when we're trying to prevent our model from overfitting, because we want to make it harder for the model to capture all specific relationships in the training data set, because we are more interested in a more generalizing model that does not really specifically estimate all the especially all the randomness in the training data. We wanted more like to learn about the general relationships, such that our model also works good for new and unseen test or validation data. Okay, so this is really all the knowledge I wanted to share with you when it comes to the discussion, the theory, and the idea behind the neural networks. So let's just go really quickly to our Google Collaboratory file. And just, I will show you more about this during the course, obviously, how you can use it. And we will always, especially in the end of the course, try to, revisit the data we already estimated with other methods and now apply the neural network. But let's first of all, if we generate some data here, so let's separate this step here. So here we will generate some data, and we will generate also some new testing data, just doing the same thing as here, but with different random numbers. Then, so let me just quickly go here. start this here, and I will tell you in a minute what I'm doing here. So what I am, let's just also visualize this at this moment. And scatter x and y, x and y test, and please just show this to us. Then what I do here is, I generate a nonlinear relationship between a single feature variable, which is in the numerical range here between -5 and 5. And this is like what I'm doing here. So we have some feature variables which are now for the moment the same for the training as well for the testing data. Then we have a functional deterministic relationship between this feature variable and the training or the testing, also between this feature variable and the target variable, which is 2 times x and the squared value of x. And then we add also some randomness, and the randomness is different here for the training as well as for then the testing data. So if we, here we generate normally distributed random variables, and if we every time we do this, Python will generate different random numbers. So the numbers we're creating here at this line are different values than we create here. You can see that on the left side is like the training data. On the right side will be the testing data. If you look closely, there are different observations here. Now, if we want to set up a neural network, then I would use the TensorFlow keras API. So I am importing TensorFlow STF, and TensorFlow has the TensorFlow keras submodule. And so for you, I could recommend 2 things. First of all, the TensorFlow documentation, which is you can find at tensorflow.org here at the API. If you go here and click on TensorFlow, then there is a really nice documentation, especially if we go here on the left, make it a little bigger, to TensorFlow keras. Then you have here nice explanations of all the submodules in the keras API. Or you could go directly to keras.io and go to the API docs and read the API docs. You have code examples here and also nice explanations, getting started and so on. But yeah, to be honest, for the moment, it's okay if you just take a look at the examples in the course here. So if we want to define a neural network with the keras API, I would say the most user-friendliest method is the sequential function that we can use. And here we add sequentially layers to our model. And what we do here, or what I like to do in the beginning here, is to add the TensorFlow input layer. And the only thing that we do here is tell keras what is the shape of the feature variables. So here we have a single feature variable. That is why we say the input shape is a 1. If we would have 3 feature variables per observation, then we would simply state that that we have 3 input shape of 3. And there is also there are models with a dimensionality higher than a 1-dimensional vector, but here usually what we are having here will be a number that is similar or identical, not similar, identical to the number of feature variables that we are using. Now, in order to let's say we want to define a single hidden layer that is like the layer that you know from the slides is in keras called a dense layer. It also has this name because if you take a look again at the visualization here, it's densely connected, meaning each a dot that we have here has a connection to all the dots in the next layer. That's why it's called a dense layer or densely connected layer. And you can do this by here the keras.layers, small capital layer, and then the dense layer. And here, if you can see it like this, The first argument are the units. Units is how keras or TensorFlow calls the neurons. So that is the amount of neurons we set. Then also you have many different, possibilities that can be set here. But most importantly, you can set the activation function by its name here. So for instance, take a look if you want to use 20 hidden neurons, and for the activation function, let's use the sigmoid function. That's the name of a name, can be found in the documentation. This is how we generate 20 hidden neurons in the hidden layer. And now if we want to have an output layer with a single output, what we do is, again, use a dense layer, but now importantly with a 1 here, meaning that the output is a single number. The activation here is the affine transformation, which is here called the linear activation function. That is also the default, so we do not really specifically define it. It would be enough if we write it like this, but it doesn't hurt if we write it here in this way, such that we really are aware what's happening here. So if we, now execute this, then obviously, as always, there's an error. Okay, because we forgot to add layers here. And the input shape is politely called input dimension. Okay, let me take a look. Input shape. Okay, maybe I wrote it falsely. Let me just take a look, because I already predefined it here, and I'm not seeing right now where the problem is. Okay, now if you execute this, nothing will happen. I mean, the model instance is going to be created, but and it will already have many attributes that we can take a look at if we use the dir function here, but it doesn't mean anything to you right now. And especially so far, our model has no idea what it's supposed to do. And to tell our model what it's supposed to do, we need to compile it. So once we define it, we compile it. And the basic information that our model needs is the loss function. It should minimize. And here we will minimize the mean squared error because we're facing some kind of regression task. And it needs an optimizer. There are many optimizers available. I don't know, but my habit is that I use the ADAM optimizer here, but you can use, for instance, the SGD, which represents the stochastic gradient descent. And there are others that you can, again, find in the documentation. Once you compile the model, now your model understands what it's supposed to do. You can also get a summary of the model with the summary function. I think you can even get this before compiling it. And now you need to fit the model, okay? And when we are fitting the model, obviously, use the fit method. We need to provide the training data, and the validation data can also be provided at the same time. I think, yeah, it's like this, which we have the same feature over, but the testing. So now we will get, the model will be fitted on the basis of this data, but the loss value of the validation data will also be shown to us. And we need our model to tell it for how many epochs is going to be fitted. For a fact, I know that for this example, we really need a long history of training. So let's set this to 1,500 for the moment. And if I now press enter, then the model will be going to start to fit. And let's just do this here. So what you see here is that you can see the loss function, how it's decreasing during training. You can see also the validation loss, which is in both cases the mean squared error here for the training data and here for the validation data. And you can see for how many epochs we are at this point. So at each epoch, as I said, we have in this case 7 batches, so 7 mini batches of equal size. So for each epoch, we have 7 iteration steps which uses a certain amount of the data in order to derive the partial derivatives and apply the gradient descent method. And after we did this 7 times, then one epoch is finished. And this is done for 1,500 times. So that's why it also takes a while at the moment. And yeah, that's just where we need to wait. I mean, I did this before, as you can see in the code below. And I did this also in another course. So let's just, while it trains, here is just for the training data. This is how the loss looks like during training typically. Here, that's why I'm using 1,500 at this one, because I know for a fact that it is kind of enough for this example here. And then you would here have the orange line, which is the predictions of our model. And you can see that it really works well in capturing this quadratic behavior here. One more information, even though I told you it is really important to standardize the data before training, I did not do this for the example here, because this example, I know that it also works fine if we do not do this, but this would be bad practice if we have real data here, okay? But yeah, I didn't want to make this more complicated than it is. And now I also forgot something, because what I usually would recommend that you save the, the history of the model which is fitted. So let me just do this one more time, and I will okay, let's just stop this, please. Okay, and now we compile it one more time, and now we start it, and we will save the the progress of the training loss and the validation loss during training here and in the history object. And then after this is going to be finished, we will visualize this. First of all, we will get let's visualize the progress of the training. So yeah, let's do this with a subplot as before, and we will use here the history. We will see if that works or if I am writing something wrong here, and label it. Well, let's make it 3. Label it with training, then the validation loss, and label it with test. Then we will scatter the training data and compare it with the predictions. So sorry that this takes a little bit. Let me take a look. Well, I'm not sure why it doesn't stop here, to be honest. Okay, seems that it stopped, but didn't train long enough here. And yeah, that would be like the label realizations. And here would have the label predictions. And if we do this one more time for the test data, then you can see that in both cases now here it doesn't work. So what I will do one more time, but maybe yeah, then make a pause of the video here, or I will leave you with that example here. So this is what I did here so far is more or less the same that I'm doing here. Here I'm just doing it for training data, for testing data. Usually it should be done, but here if you simulate it will be the same. If we simulate it in the same manner, you know, using the same relationship here. And as you see here in our example, okay, I use a little bit more than the neurons here, but I know for a fact that most importantly here is that we train the model long enough. Setting it to a verbose here of 0 leads that you know, it doesn't print out the information during the training process, but then after the model is trained, we can take a look, as you can see here, and you can see here how it works very fine. But you can also you know, use this code and play around a little bit. You know, if you use lower amount of neurons here, you can use, for instance, here different activation function, and also if you use a lower amount of epochs that is going to be used for training, you can see, or you will see, that this the model fails to approximate this relationship. So hopefully it will, you know, provide or give you information that it is also, yeah, kind of sensitive what we're doing and defining here. But nevertheless, sorry this took so long. Most important for me is that you can see here that it's kind of comparatively easy to define the neural network, to compile it, and to estimate its parameters, and then, like, step by step, especially with the applications that we're going to use during the course, you will, you know, like, learn more and more how you can apply that on your own. And that was not the important aspect here, because otherwise you would have decided to choose another example here. So yeah, I will run this code one more time, and you will find this output also in the additional code file of your collaboratory. So yeah, I think the video now is really long enough, and I hope also that you have at least you know, like, the basic understanding or an idea what the neural network is, and you already seen how to use it one time, and that's like, this should be a starting point. You know, and you do not you know, your mindset now should not be that you should have already understand all those concepts, because I think then you would really need to spend way more time here, and it's also quite challenging and demanding at your current situation that you really understand all this in detail. But this is meant to, you know, show you the relationship to the more basic models we discussed in the beginning of the course, and is also meant to give you already a powerful model family that you can also define by yourself, that you can try and play around a little bit and use them for the examples that we're using during the course. And hopefully that will give you a good foundation to have a good starting point once you are, you know, really excited about neural networks and want to learn more about that. Okay, so this is like, that's the intention at this point in the course here. Okay, so that brings us to the end of the supervised learning part of the course. And now in the next videos, we are going to take a look at you know, 2 topics of unsupervised learning. So hopefully see you soon in the next video, and until then, have a good time. Bye bye.